So, it's 3-something in the afternoon, so I thought I'd get into something really serious here, right? So we all know what's coming up on Sunday. I mean, the real important thing this week, forget about the elections. This is what's really important.
Is that the one with the round ball or the oblong ball?
Which version of football are we talking about?
Sports ball.
Are there any? Yeah.
Oh, is that where they score the points?
Exactly.
And try not to kill each other. Any Panthers fans in the room? Oh, come on, I know one. You gotta at least raise your hand halfway.
Me?
Yeah.
Broncos.
Oh, there we go, okay. Any Broncos fans? Okay. Any Dallas Cowboys fans? Oh, come on, and the room's gotta be full of them. Well, there's a reason we bring this up, and it's a little self-serving here, but turns out that the 49ers run our product. They use all of our product, there's storage in the storage arena. They have 70 terabytes. They use it for everything, including stats analysis, which is why they chose us, because we're extremely fast. We have low latency. They can get the information during a game, bring it up to your screen almost instantaneously. It just so happens that the Levi Stadium is right behind us, right behind our headquarters. You can literally walk there, and they got a great bar down underneath. So for us, it's really good. It's really good. And of course, I want to mention one thing. I didn't get invited to the box. We have a box at the stadium, but that never came through in the email. So, as you can see, we keep our name up in lights above the stadium. We're really integrated well with the 49er organization. They support us, they endorse us, and vice versa. So, it's a nice story going forward. So, I don't know how much of this exposure we'll get at the Super Bowl, but just remember, when you're looking at Levi Stadium, thinking of the great environment that they have there, that we keep it up and running. As you can see, all flash storage. And all flash storage is our game. So we don't have any hard disk, any spinning disk in our product, and we don't have any SSDs. We're strictly flash-based storage, true flash-based. We write right down to the NAND level on the chips. There's only 2 companies right now doing that. Purely, that's not pure, that's us and IBM. So we're the fastest array on the planet right now. We are the pioneer, by the way, and that's why that slide's there, just to let you know, we're the pioneer. We started on all flash storage, and back in 2009, we released the first version of our current platform. And we build up from there. So we're not buying somebody else, we're not relying on SSDs as a third-party source. We developed a product from the ground up, and we did so with a real good heritage of having flash cards before that. Also, we have as a very strategic partner Toshiba, who we get our chips from. So we're staying right on the bleeding edge of the architecture as it goes forward. We'll talk about that a little bit more in a minute here. So lately what we've seen is our customers going out and saying, hey, can I actually bring flash storage into the data center as my primary storage array? I've been using it. We've got some really high-end customers. I've been using it because it's been a pure performance play. You know, 1 million IOPS these days really doesn't seem to be that great of a deal anymore. A lot of people do 1 million IOPS read. Not too many do that kind of sustained write rate, and I'll talk about that in a minute. So now that that has become kind of common language and the data centers that need that kind of performance, how can they add additional features? Can they get more money out of that array that they've purchased? So what that's doing is driving companies like ours to add data services, and we have. So now, besides having the typical checkboxes of snaps and clones, et cetera, we now also have a full suite of data services that go along with it. It brings more value to the product. And the reason it brings more value to the product is important is because the cost of the product is starting to drop. So these days, if you take a typical flash storage array and you run deduplication and compression on it, and you do an analysis of what your effective cost for storage is, that is, after it's been deduplicated and compressed, now you're looking at storage that actually costs down at $1 to $1.50 a gigabyte. So now we can actually start to compete on cost with the mainframe arrays that are out there, the VMAXs, the VSPs, et cetera. So we're down in that price range now. Not just us, but also our competitors. So flash storage is starting to move into the data center. We're seeing customers of ours actually start to use it as their mainframe storage, not just as a high-performance play. This is what our storage portfolio looks like. The 3 boxes, basically what we're doing is aiming at 3 segments of the marketplace. The 7250, our latest product, is aimed at those folks who would like to be in at under 100K and would like to run deduplication and compression. It's a large marketplace out there. We do so, and we do so at 250,000 IOPS sustained, which is pretty impressive, and it keeps the cost down. So what we're allowing here is folks to be able to start moving into the flash storage arena, try it out, see how it works for them. Nobody's going to complain when they see the type of performance they're getting. And as they take a look at it, they can start to move up the stack. Maybe they'll go move up into a 7300, which runs our mixed workload, which is a mixed workload box. So our products all run mixed workloads. What we're really good at is random IOPS, random IOs. That's something that some of the products out there aren't that good at. What that means is you can mix workloads. It also means you can go into a data center environment and you can start to separate out users, applications, business center functions, and maybe even separate clients, because we do allow storage containers. The 7600 is our top-of-the-line product. It's a pure performance play. It runs over 1 million IOPS at less than a millisecond. The latency on the box is actually about 150 microseconds, extremely fast. We have a lot of clients running this box out there, our products out there. So it's not unusual for some of our clients to have 100 arrays out in their data center. If you need to scale up, well, we have to have that ability now. We have to add the value into the data center. We have a product, our 7700 controller, which allows us to stack up to 10 arrays underneath the controller. A set of these controllers can be configured into an HA environment where we can actually do LUN mirroring. We can do asynchronous, synchronous replication. We can do a stretch cluster with full LUN mirroring and 100% failover capability. So this is basically what it looks like. Let's get into the technical stuff a little bit. So we have our graphical user interface, which is an XML-based browser interface, which runs from anywhere, that actually manages our array and all the components of our array and all the features and functions, and it doesn't matter where the arrays are located. That's kind of what it looks like in the upper right-hand corner. It has all the bells and whistles that you're going to need or expect in a management product. Now, there's been a lot of discussion today about cloud. We do have clients that are running our product in a cloud-based environment, not just in a local private cloud, but also in a much larger private or hybrid cloud. And they do that because we're fully integrated with the products you'd expect. We have complete VMware integration, EAAI, SRM, VASA, all that you'd expect. So, but that's into the local private cloud. If you want to go out, you want to go into, say, OpenStack, or go out, take your data out into Azure, maybe, or out into AWS. We have full REST API implementation. Basically, I have two sets of APIs. One is your basic API for your typical XML calls to get information from the storage array. We have another set of APIs which give us your entire suite of functions that are available from our product. So we have one customer as an example who has something in the neighborhood of beyond 50,000 virtual machines running an OpenStack, a financial services customer. And it's all done using the REST API and integrated with our particular product through the Cinder block access method in the Juno release of OpenStack. So the REST interface, if you're not familiar with that, that opens us up to pretty much everything. EC2, Azure, Oracle, MySQL, MS SQL, and Oracle all have REST interfaces. Our system, we have a System Center Operations Manager, a management pack that also uses REST to be able to manage our arrays through System Center Operations Manager. So it's pretty much everything there that you need to take the product into the cloud. Like I had mentioned in our panel previously, what you really need to do if you want to go into cloud, if the application and users want to go into cloud, we need the application then to be able to come out and take the information from us, as our customer who's using the 50,000 VMs does. Our operating system, Concerto OS, which is a Linux derivative, also has complete REST API exposure. So Concerto OS is what runs on our memory gateway. Our memory gateways are typically what you would call a service processor and one of the major competitors. In that layer, we run all of our services, which is synchronous, asynchronous replication, HA, thin clones, full clones, snaps, the full work. Everything that you'd expect in a storage platform is run under our Concerto OS. And then, of course, down at the lower level, we have our flash array, and I'll talk about that architecture in a minute, which talks up to Concerto OS. So this is the heart of the system, the Violin Intelligent Memory Module. So it's our equivalent, and I want to use a comparison to what someone would have as an SSD. The difference, of course, being that it's not an SSD. We're not handing off control of garbage collection or the chip, the flash end writes to somebody other third-party product. We build it from the ground up. Our whole system is built from the ground up. So what we've got here is a particular customized Vim, it's called, equivalent to what would be a disk drive or an SSD. So it's extremely powerful and fast. As we said, we build it from the ground up, so we're not looking at some type of technology we need to incorporate from some other vendor. The architecture is extremely resilient. We basically have, there's 3 ported paths to every single Vim out there in the architecture. So things happen like there's no write blocking for RAID groups, if you're familiar with that. There's no delay time when you write to wait to do a read from a RAID block. So we're really at the state of the art here. Now the design is also built so that we can upgrade. When Toshiba gives us a latest chip, we're ready to go. We don't have to basically rebuild the whole product. What we do is we just change the microcode that sits out on the Vim. So right now we're running the 2 terabyte. We're running 2 terabyte Vims. We're looking at 4 terabyte Vims here in sometime this year. We're also in beta working with 3D chips from Toshiba, 3D NAND. And we're also looking at Crosspoint, which was talked about in the session here a while ago. So what that means is capacity is going to go up, so cost per gigabyte is going to continue to go down, and performance is going to also increase. So with the 3D chips and the Crosspoint chips, what you're effectively allowing is a 1,000 times increase in latency and performance access down at the NAND chip level, 1,000 times. So right now these products are extremely fast and writes. It's questionable how fast some of them can be, but as we get into Crosspoint and 3D, you're going to see the performance increase even more. At that point, you've got increased performance, increased capacity, increased capability of the product. So it's going to keep driving the product's flash arrays down into the data center because it makes more sense. And of course, everything is hot swappable in our product. We'll talk about that in a minute. So this is what we start out with. We use all Toshiba chips at the NAND level. Then we incorporate them into our Vim. We put them into a proprietary RAID configuration. Kind of looks like a 3+1 or a 4+1. Kind of looks like a typical RAID group, but it's not quite the same. And that's because we don't allow write blocking. All of those are packaged into our 3U package, our 3U frame. All of our products run in a 3U frame. No need for battery backups stuck underneath. Basically what happens is our product is capable of flushing everything out, still sitting there for 50 milliseconds. So 10 milliseconds is all it takes to flush everything that's in the pipe, because we're not using SSDs and we're not using any huge DRAM cache in the front of our box. It's all right down at the Vim level. So we can flush everything that's in line at 10 milliseconds or less. No issue with power failure. We never lose data. We never lose power. No battery backups. Like I'm saying, this thing is really state of the art. Coming from me and seeing Hitachi, I really appreciate this stuff. And it all builds up into our 7700. So if you want to do an HA configuration, stretch clusters, LUN mirroring, we've got all that built. We can give you basically full redundancy. I'm not going to talk about 5 nines and 6 nines because I think that's a bit exaggerated. But basically, if you actually do have a failure or something does fail, you're not going to lose any data. This is what the box looks like. So what we've got here is our memory gateways. These are basically Intel servers running Haswell processors. Now that's where all the data services are. So everything comes in there. It may get deduplicated, it may not. And then it's passed along into these array control modules right here. And that all comes in and basically comes in on a PCIe bus. So once the information hits the front of the memory gateway, it's already into a fully redundant mesh PCI configuration. So once it gets into the ACMs, it then is passed out. I guess we'll flip these all up here for a second. Into our PLX switched backplane. Fully ported, complete grid mesh backplane. We've got triple ports to every single VIM that's out there. And there's 4 RAID controllers, fully redundant. One of the things we do to improve performance is we basically stripe the RAID groups across whatever we need to in the array to maintain that redundancy. It also gives us extremely fast performance, both on the read side and the write side, because we're not waiting for one single path to read that information while somebody's writing to that RAID group. It's all, as I mentioned, the array controller modules are active. So this is what we've added on top. This is our stack. So we took the basic information that we have, which is a super high-performing box, and we decided, hey, what kind of additional features can we add in? So this is what we've got. Stretch cluster, which happens to be my baby, which allows us to put together a mirrored LUN configuration at fiber channel or iSCSI 10 gig E distances, typically inside of a metropolitan area network, with full redundancy. Basically, the LUNs are mirrored. So you have 2 boxes, similar boxes on each side. They're mirrored across. There's full redundancy. They can read and write in either direction, and you have complete failover protection. Synchronous mirroring. If you don't want to go into a full HA, we can actually do synchronous mirroring. We can do asynchronous replication just from array to array. So if you have 2 boxes and you just want to do asynchronous replication, and just to have some backup, it's there and it's free. We don't charge extra. So you're not talking about a whole bunch of licensing levels on top of our products to get what you need in the way of high availability. And here's I'm not getting into this too much, but just some of the service we have. It's extremely incredible that we've thrown all this into the box. To me, it's like before, when I was at EMC, we had to have, to do some of the stuff, we had to have VPlex, we had to layer on top of that recover point, do a stretch cluster. I mean, some of the things that had to do with the other products out there. And then I walk in here and Violin, we said, hey, it's all basically built into the operating system. It's all in Concerto OS. So one of the things that's quite important that I'd like to point out is this is a feature that I don't know who else has this, granular deduplication. So let's say you got a box, say you got a data center, and you've got an Oracle OLTP database that you're running. It's got to have extremely fast performance. You want to run a thick LUN out there. So what we do is, okay, set up 2 storage pools. One storage pool can be for your high-performance arrays. You can run your OLTP through there. Put some thin LUNs in there if you want to. Let's set up another storage pool, and let's call it a deduplication storage pool. So if you have, say, SharePoint or email or Word information out there that you don't care about the super fast performance, which means if you can only live with maybe 500,000 IOPS, we're going to take that information, put that into a separate storage pool, and deduplicate it, and just keep it around. Okay, so we've done that on a LUN basis. Now, who else can do that? I mean, granular deduplication on a LUN basis inside of the same array, that's pretty slick. If you want to move data back and forth, let's say that all of a sudden that particular set of data needs to be brought back into high performance. Well, you create another LUN over in the other storage pool and copy the data over. And of course, we do all the check boxes you get in storage: thin provisioning, thin clones, full clones, snaps, what you'd expect to see in any storage array. Now, the box is completely HA, completely redundant. Everything's redundant. And everything's hot swappable all the way through. Because of our complete grid mesh design, you pull out anything in there and nothing stops. You don't lose any data. So say we get a call home message that there's a problem with one of the NAND chips in one of the VIMs. The box is already proactively moving information off of that VIM to another VIM that it has. So we've got complete redundancy there. So you don't lose data. So this is what you run into. This is the main differentiator here between our product and some of the SSDs that are out there. Is we don't run into the write cliff. And the write cliff basically means when you start to pump a lot of information into a flash storage array, you run into the issue that writes take 1 to 3.5 milliseconds at the NAND level. That's really substantial. We hear all the stuff about 150 microseconds. That's read performance. Try doing that with the write performance. So in our particular case, we built the box with redundancy and mesh architecture. We don't run into that. So we start to put the information out in the array, down at the VIM level, into DRAM, and we write it to flash. So our write throughput is basically the highest in the industry because we don't run into this write cliff issue. I mentioned this once before, so I'll just flip through this. What did I do here? And with that, I've seen the 5-minute clue. I'll wrap up and ask if there's any questions.
Which flash foundry do you use for the actual physical flash part?
I'm sorry, I just got off the airplane with a head cold. I can't hear a thing.
Sorry. Which flash foundry do you use for the actual flash modules themselves? Not all the control logic, but
The chips themselves, the NAND chips, are Toshiba's. Toshiba owns 10% of our company, so we kind of got an inside track. And so the 3D that's coming out,
Yep.
we already got it in our hands. Any other questions? No? Okay, I guess we're all set. Thank you, everyone.
Thank you.